Hello and Assalamu alaikum to each and everyone. My name is Elizabeth M. Datumanong, and now we will be discussing the Poisson distribution. So let's look at an introduction to the Poisson distribution.
Suppose we are counting the number of occurrences of an event in a given unit of time, distance, area, or volume. So for example, we might be counting up the number of car accidents in a day, or the number of dandelions in a square meter plot of land. Then, the number of event is going to be a random variable that may or may not have the Poisson distribution, depending on the specifics of the situation. But the Poisson random variable is a count of the number of occurrences of an event. So here is the probability mass function for the Poisson distribution. The probability the random variable x takes on the value little x, which you'll sometimes see written as p little x, is equal to the lambda to the x times e to the negative lambda over x factorial. E, like pi, is an important mathematical constant and the base of natural logarithms. It is approximately 2.7182, but it is an irrational number that has infinite non-repeating decimal places. We have a background on factorials, but as a specific example of this x factorial, 5 factorial would be 5 times 4 times 3 times 2 times 1 would be 120. It's not a probability distribution until we say what values x can take on. Here, the random variable is a count of the number of events in a given unit of time. And so, it can take on any non-negative whole number variable. For any value of x that is 0, 1, 2, up to infinity. There is no upper bound on the value that x can take on. But depending on the situation, the probability is eventually the mean of the Poisson distribution is lambda. So, mu, the mean of the random variable x, is equal to lambda. So, we could have used mu as our parameter, and some sources do that. So, the variance of the Poisson distribution, which we'll label as sigma squared, is also equal to lambda. So, let's look at an example. So, for the first example, 1 nanogram of plutonium-239 will have an average of 2.3 radioactive decays per second, and the number of decays per second. And the number of decays will follow a Poisson distribution. Now, what is the probability that in 2-second period there are exactly 3 radioactive decays? So let x represent the number of decays in a 2-second period. Lambda is the mean number of decays in that period. So here we have an average of 2.3 radioactive decays per second. We are talking about 2-second period, which is going to equal lambda is going to be 2.3 times 2, which is 4.6. So we want to find the probability that the random variable x takes on the value 3. And the Poisson probability mass function is lambda to the power of x times e to the minus lambda over x factorial. And here that's going to be 4.6 lambda raised to the power of 3 times e to the negative 4.6 divided by 3 factorial. So if we work that out on a calculator or computer, we see that that is equal to 0.163 when rounded to 3 decimal places. So, as you can see yan po. So, that is the probability of getting exactly 3 radioactive decays in a 2-second period.
So that would be all, and thank you for listening. Bye!